So in this example, what we need to do is use what we've derived already in order to find another angle, this time for an archer who intends to shoot an arrow to clear a wall. And it says that the arrow is fired from a point O with speed of 50 meters per second. Okay. Don't forget, it says a point 5 from a point O. This will relate to where we have to put our reference system in, which I'll do in a second. And then we're asked, what's the angle? The archer should fire this in order to clear a wall whose height above a horizontal passing through O is 20 meters and has a horizontal distance from O of 40 meters. All right then. So here you can see this diagram with the archer ready to send an arrow in some direction. You'll notice that I've marked out this horizontal, which intends to be from the point O where it's fired from. Okay, so in this diagram, I'm going to put the reference system exactly here on my diagram. Okay, and then what happens is this arrow is somehow given some speed. God knows what it is at some angle. Oh no, we do know the speed. Sorry, we don't know the angle. So the speed is 50 meters per second. And the question is, well, how do we clear a wall which is 20 meters above this horizontal and 40 meters from the point from which it's fired? Right, so in order for this arrow to clear the wall, it's preferable that when the arrow is either going up or coming down, it's able to clear this point at the tip of the wall. So this point is as a coordinate in X and Y axes. This will be 40 across and 20 up. All right, so at some time t, our capital T, our arrow has to clear the point 40, 20, or at least be passing through the tip of this, which is the tip of this wall. This is our wall, the tip of the wall characterized by this coordinate. So this means that there is a time, capital T, where the position vector r is 40i plus 20j. Right, okay, so don't forget, so we know that the speed, u, is 50 meters per second. The only thing we don't know is the angle alpha, and we know g. So we're looking to use this formula here. Right, so if I equate star and double star, at time t, capital T, I get, or we get this following, this vectorial equation. So it's 40i plus 20j is equal to, now I'm going to sub in what we know. So u is 50. Capital T, cos of the unknown angle, times I. And then we have plus minus g t square over 2 plus u capital T sine alpha unknown. So we get this. So vectors only equal if the components equal. If the components are equal. That's That's the gag for this one. Okay. Now, this implies that we have the following equations. 50 capital T cos alpha, it has to equal 40. And then this one, which corresponds to equating the second components. Now, it's slightly different from last time. You notice, by the way, notice that I didn't put 50 in for the initial speed. Okay, so that's 50 t sine alpha. Alpha's unknown, and this should be equal to 20. Okay, so, well, what about it? So t's an unknown and alpha's an unknown so far, but the first equation gives me a way to get hold of t. So if I just copy this across, I have the following from 1. The capital T is 40 over 50 cos alpha, which is 4 over 5 cos alpha. It's sort of similar to last time, what we had, you know, the method, except you'll see there's a slight difference at the end. So this is 3, then 3 in 2 gives me the following. So I have minus g over 2, 4 over 5 cos alpha square, plus 50 t sine alpha equals 20. All right then, so what else? Okay, so as you can see, let's multiply both sides. Multiply through by 25. You know what? Let's do it by 50. Let's do this by 50. Because this will be 5 squared in the denominator, multiplied by 2, so that's 25 in the denominator of the first term, is this. So when we do this, okay, what we get is the following. We get minus, now 16, because that's 4 square, g, plus, now 2,500. You know what? I've forgotten to put in capital T. Okay, let me just correct this. Okay, so this needs to be 4 over 5 cos alpha. Right? Good. So it's not 2,500. Okay, so what is it? Well, I'll have 50 multiplied by 4. Now there's a 5 cos alpha in the denominator, and we're multiplying by 50 cos squared alpha. So this gives me 10 cos alpha sine alpha. Okay, equals then 1,000 cos square alpha. Okay, so now what we need to do next is, well, clearly we can do some simplification here. So this is what, 50 times 4 times 10, so that's 50 times 40, which gives me 2,000. All right, so what we've got is 16g plus 2,000 cos alpha sine alpha equals 1000 cos square alpha. Okay, so next, it looks pretty impervious at the moment. Looks really, really tough. I mean, what we're after is we need alpha. Remember that the goal is to get alpha. And we have this cos square, and we have this cos square alpha and cos alpha and sine alpha. So looks pretty tough. Okay, so what I propose is, well, remember this. So let's divide by now. Let's divide by cos square. Actually, you know, you'll see that we'll return back a few steps. But anyway, so we have 16g 1 over cos square alpha plus 2000. Now I'll have cos alpha sine alpha over cos square alpha, just gives me this, equals 1000. Okay, good. So remember this, cos square alpha plus sine square alpha equals 1. Now if I divide through by cos square, I'll have 1 plus sine square alpha over cos square alpha equals 1 over cos square alpha. And this guy is tan square alpha. So, good. If I plug this in, what I have is, of course, let's put it in this equation. If I plug this in here, we get this minus 16g. 1 plus tan square alpha plus 2000. Now sine alpha over cos alpha is tan alpha, and you have 1000 there. Okay, good. So after this, you can see I can rearrange this. So let me take this across and rearrange. Okay, so here, now I can get this. I can get minus 16g. He says rearrange. It's not a big deal. Minus, to rearrange this. So we get this. Then the next term is this. Then, now I'm deliberately choosing the structure of the equation for this. Okay, so I've subtracted 1000 one side from both sides, and now what I have is the following. Now, let z equal tan x, and you'll see that now this reduces to the following: minus 16z squared plus 2000z minus 16g minus 1000. Okay, so this is now equals 0. This on the left is a quadratic in z, and we can solve using quadratic formula. I mean, it's up to you. You can write this in the symbolic form using completing the square, but really it's not necessary. I mean, you'll have to compute some numbers anyway at the end. So use the quadratic formula. All right, so if you do this, okay, so let's do this. So z plus minus is minus 2000 plus or minus the square root of b squared minus 4 times minus 16g, and then multiplied by c, really nasty numbers. But anyway, as I say, we're just going to throw this in to a calculator, which we can do. And then all divided by what? All divided by minus 32g. Okay, so if you do this, I'm now going to just head to the computer and pray to God that we get something sensible. So I'm going to ask the computer to solve this equation. So I have minus 16 times g. Okay. Times z squared plus 2000 times z minus 16 times g minus 1000 equals 0. Okay, and what pops out from this, hopefully you'll have got these answers, what you get is z equals 0.67. Now again, what I'll do is the following. So z minus, or the values of z from this, let's put it like this. Because I think z minus is actually the highest value according to this notation. So I think this is z plus, z minus, right? So this is to 3 decimal places. Z minus is going to be 12.135. Now, I'm keeping this again as full precision, but note that Z, recall, Z is tan alpha, tan of the angle that we hope to pitch this arrow to clear the wall. So now we have the following equations to solve. So we have tan alpha plus, which is the alpha plus value that corresponds to this. Tan of alpha plus equals 0.67. Again, I write simply for presentation purposes these equations with 3 decimal places, but when I compute, I'll do everything with full precision. Okay, so from this, now remember that okay, we simply have to invert tan here. So tan inverse, and I'll be doing the computation in radians. So tan inverse of this will give us our second angle. So if we do this, we should catch an angle. Remember that alpha has to be between 0 and 90. That's what I was trying to say before, or which is equivalent to this, alpha in radians. So we get alpha plus. Now let me just move to the computer. Alpha plus is arctan. In radians, I get 1.489 radians. Alpha minus, which is clearly between 0 and pi over 2, something like 1.57. Alpha minus, let's do the second. That's wrong actually, I've mixed the values up. So that was alpha minus, apologies. Now alpha plus, well, just get the lower value. Okay, and again, this is also in the desired inequality range. Okay, to 3 decimal places. Remember that I've computed this with full precision. So finally, if you want this in degrees, just to get a feel for what this really is, in degrees, alpha plus is as follows. So alpha plus, I should divide by 2 pi and multiply by 360. This will give me what I need. So this one's 31.276 degrees. again to 3 decimal places to 3 dp, and alpha minus, right, let me just do this one, alpha minus, if you do alpha minus you'll get 85, which is quite high, but it corresponds to probably a very steep trajectory which reaches a high height and then is coming over the wall on its way down. So this is 85, 289 degrees to 3 decimal places. Okay, so well, there you go. Actually, it ends up that you have 2 choices. So the answer is we have 2 choices for the angle. Not just one. So you have 2 choices. So you can calibrate your shot so that it clears this wall in one of these 2 ways. Okay, and that's really it then for this example. And next we'll look at some cases when we have time-dependent forces. So see you soon.